Actually, so I got the desktop on now. It was off, so I thought. Okay, this was in here. I don't think they can fix it right away. I think they need to actually replace the connection between this box and the projector. But actually, you can, if you want to call them again, you can let them know that I can't probably do it during lecture, but and I got the system PC working. But they need to fix that connection because I need to use my laptop eventually, next class. Thanks. Okay, let's get started. I'm sorry for the delay. There's still, the laptop connection still doesn't work. So, and this time the PC was also powered off. All right, everybody, be quiet, please. I want to get going. All right, quiet. So this is actually, I think this is a really interesting topic. So last class we talked about interest point detectors, which is detecting points that you can track or points that you can match across images. And in particular, we talked about the Harris corner detector, which is very relevant to today's lecture. And we also talked about difference of Gaussian detectors, which are more used for long-range matching. One thing to note is that I link to papers with the lectures often on the website, and I generally recommend that you read them. All those papers are really amazing papers, or at least very important. And in particular, I want to emphasize that you should read SIFT. SIFT is probably, it might be even the most cited paper in computer vision. But it's kind of it's a very engineering-y paper in the sense that it just it gives some kind of motivation for what they're trying to do, but then it goes through all the different design decisions and kind of goes through a lot of testing to try to find a descriptor that works well. So this class, we're going to talk about tracking features in a video. So you assume that the features that you're finding correspondences between haven't moved very much between images or between frames. So we want to extract visual features and track them over multiple frames. And then a very related problem is optical flow, where you want to be able to say where all the pixels from one image have moved to the next image. So I think this paper, this is based on Lucas Canati, an iterative image registration technique with an application of stereo vision. It's only a 6-page paper, but it kind of solves feature tracking optical flow in stereo. So it's the most dense value per word, basically. But it's also really easy to read, I think. So you should definitely read that. It's pretty amazing that they, basically because all these problems boil down to finding correspondences, and the paper addresses the problem of finding local correspondences in a very general way. So, so the idea of feature tracking is that many problems like structure from motion require matching points. You need to find points in one image that match another image, and you need to find these matches across multiple images. And if the motion is small, if you haven't moved a lot between frames, for example, if you have a video, then tracking is a good way to get those points. If the motion is large, then you kind of have to rely on a different method because you don't have some prior about where those points are likely to be. So for example, so this is just showing two images of a sequence. This is actually like a large time step between them and a set of key points, and you'd want to track these points across the sequence. So, so what are the challenges? One challenge is that you need to figure out which features can be tracked. This is kind of what we addressed in the last class. You need to be able to efficiently track across the frames. Efficiency is often important because you might have a real-time application, or at least you're typically dealing with a video sequence, so you've got a lot of images to analyze. Some points might change appearance over time. So the object might rotate, it might move into shadows, and so that can create difficulty in matching points between consecutive frames. And then a significant problem is drift. So drift means that you might have a small error from frame to frame, maybe just a pixel or half a pixel. But what can happen is that if you're half a pixel off on frame 2, then you match that region that's half a pixel off, and then maybe you're a pixel off in frame 3. And over time, your points can latch on to the wrong features. So drift means that small errors accumulate as the appearance model is updated. That happens very frequently. And then another major difficulty is that points can appear or disappear. So just a point that you're tracking might move behind the object, or the object that it's on might rotate. Hi. Yeah, so I got the PC working. The problem is that I tried a couple different laptops and both connectors. The box is receiving the signal, but the signal is not going from the box to the projector. And so I really need it fixed by Tuesday, because then I'm going to need to use my laptop to do some demos. Okay.
I'm guessing now is not the good time.
No, not now. I just wanted to make sure, because I had somebody come the last 2 classes and it never got fixed, so I just want to make sure it gets fixed. Thanks. Thank you. All right, so feature tracking. So the goal is, given 2 subsequent frames, estimate the point translation. So here we've got some image, and the notation is ix of t, means that I've got some point at position xy at frame t. And these points move, so that in the next frame, t plus 1, so then I have, so at the next frame, t plus 1, all the points have moved. So I want to be able to say that I want to estimate this displacement for each point, so basically a uv, so that at the next frame, I have x of t plus u, y plus, I of x plus u, y plus v, t plus 1. So there's some key assumptions that we're going to use to be able to track these points. The first is called brightness constancy, and that's the assumption that the projection of the same point looks the same in every frame. In other words, the pixel intensity of the point that we're tracking won't change between consecutive frames. And that's a really crucial assumption that we'll rely on. Another assumption is that there's a small motion, so points don't move very far. And then a third is spatial coherence. That means that points move like their neighbors. So it's not just every pixel isn't just moving completely randomly. If some pixel moves 3 pixels to the right between frames, then its neighbor will probably also move about 3 pixels to the right. So the brightness constancy constraint is really the most fundamental assumption of the algorithm. So the problem is that we've got some pixel xy, and it's displaced by some uv. So that means it's moved u in the x direction and v in the y direction. And so now it's located at x plus u, y plus v in frame in the t plus 1th frame. So the brightness constancy equation just says that the intensity at xyt will be the same as the intensity at x plus u, y plus v, t plus 1. So the pixel didn't change, or the point didn't change its color between consecutive frames. So we can turn this into a constraint that's useful to us by taking the Taylor expansion of x plus u, y plus v, t plus 1 at x, y, t. And I'll go through, I'll just show this, and then I'll illustrate why it actually makes sense, because it's not very intuitive. I think the end result is not something that I would guess without going through the math, but then I'll show why it kind of makes sense when you visualize it as well. So, so Taylor expansion means, so you've got the Taylor expansion of this function at xyt is the x derivative of the function times x plus u minus x plus the y derivative of this function times y plus v minus y plus the t derivative of this function, which means the difference between consecutive frames in this case, the difference of intensity between consecutive frames, times t plus 1 minus t. Okay? So that gives us xy, I of xyt, which is the intensity of the point at frame t, plus the derivative of the intensity in the x direction times the u displacement, and u and v are what we want to estimate here, plus the derivative of the intensity in the y direction at that pixel at xyt times the v direction, plus the difference of intensity at that point. And note that I'm dropping out the, this is the gradient at xy. This is the gradient at xy, and this is also the time difference, the difference of intensities at xy. I'm dropping it out because there's going to be a lot of these ix's and iy's, and otherwise there'd be letters all over the place. So it's the gradient in the x direction times u displacement plus y direction times v displacement plus the difference of intensities over time plus the original intensity is equal to the new intensity, okay, from that linearized Taylor expansion. So now I can just bring over, so note that this is known, or no, this is, this is known because we're saying that it's going to be the same as this. But bringing this over, I've got the intensity where I track the point minus the intensity where I initially observe the point should be equal to this, right, by Taylor expansion. And because I'm saying that these are the same by the brightness constancy equation, that means that the intensity, the derivative at x, the derivative of x at xy times u plus the derivative of y times v plus it should be approximately equal to 0. In other words, I want to try to solve so that it is equal to 0 or as close to 0 as possible. So this is just another way of writing it in a more compact form. So the gradient delta I here is, or del I, is the gradient in the x and y direction. It's a tube vector. Dot the displacement, which is what I want to solve for, plus the difference over time should be equal to 0. So this gives us a constraint that we can use to solve for u and v. How many equations and how many unknowns do we have per pixel here? How many linear equations and how many variables? Yes?
One equation, two unknowns.
Right, we have one equation and two unknowns. And so that should tell us that we can't solve it yet. We don't have enough constraints. So in particular, the component of motion that's perpendicular to the gradient can't be measured. So if you think about it, if u and v satisfies the equation, then so does u plus u prime, v plus v prime, as long as del I dot u prime v prime is equal to 0, right? Because if I add u prime and v prime to u, but del u prime v prime is equal to 0, then the equation will still give the same result. So in other words, if my estimate is, if the correct value is uv, but I add any u prime v prime in the direction perpendicular to the gradient, then it's still going to give me the same, it's still going to satisfy this constraint so far, right? And so I'm not going to be able to estimate it yet. And so this is something that's called the aperture problem. And I can illustrate it just by showing, so here I've got a line that's moving up into the, or I guess it's moving down into the right. Right? It's clear to see. And it's still same motion, but now I just blocked out the outside, right? And now it looks like it's moving up into the right. So here you've got a lot of points here along this line, but you can't really tell the motion because you only have, because all the gradients of these points are the same, right? It's just a straight line. So if I go back just to this, now if you try to oops. So try to look at it, try to ignore the part that's outside the circle, and you can see that the motion is the same. If you look at just the points inside the circle, then it looks like it's moving up and to the right, but when you look at the whole line, you can see that it's moving down and to the right. And then a similar illusion is called the barber pole illusion. So right now it looks like it's moving diagonally down and to the right. Now it looks like it's moving like straight down, probably. And so this is something that it's called the barber pole illusion because barbershops used to have these on the outside sometimes. So this looks to me like it's moving upwards, but it's actually just moving horizontally. And it's because you only see part of the shape at a time, and all the gradients are in the same direction. And so you don't have enough information to disambiguate it. So if you look at just this part here, you can see that it's actually, another valid interpretation is that it's moving left to right, which is actually what's happening. Because obviously there's no way for it to, there's no way for it to continuously move upward, right? All right, so how do we solve this ambiguity? And this is what the paper addresses. So basically, we need more equations per pixel. There's no other way around this. So this is where the spatial coherence constraint comes in. So as long as, if we can say that the pixel's neighbors also have the same displacement, then that gives us one constraint per pixel, and we still only have two displacements. So for example, if we use a 5 by 5 window, so if we say that a 5 by 5 patch around the pixel all moves with the same displacement, then that gives us 25 equations per pixel. So now our system is overdetermined, which we like. So we can do a least squares solution. So here we have 0 is equal to the difference of pixel intensity over time at each point in the patch, or at a particular point in the patch, plus the gradient of that point dot with u and v. So just in case you're rusty on notation like dot products, AB dot CD is AC plus BD. So if I then write these down as a system of linear equations, I've got one equation per pixel. So I've got IX and IY of the first point in that 5 by 5 patch times UV, and that's equal to minus IT of that point. So I'm just moving the IT over to the left side. So I've got a set of knowns here. Knowns, I know what these values are. I know what these values are. And so this should be kind of familiar if you ever solve systems of linear equations. You've got something in the form of AX equals B, where A and B are known, and X are the variables that you're solving for. Right, so here it's written as AD, D for displacement, is equal to B. Right, and so if I want to solve this, I can solve this with a pseudo-inverse. So I pre-multiply both sides by A transpose. This gives me a square matrix so that I can potentially invert it. And then I have the solution is D equals A transpose A inverse times A transpose B. That's just the pseudo-inverse. Right, now if I do A transpose A is actually just the sum of gradients over the patch, the sum of x gradients over the patch in the upper left part of the diagonal, the sum of y gradients over the patch in the lower right diagonal, the sum of x gradients times y gradients over the patch in the off diagonal. And then the A transpose B is just the sum of x gradients times the difference over time, and the sum of y gradients times difference over time. So note that the summation over these, the summation is over all the pixels in the k by k window. So I'll do a little bit of illustration in a moment, but I'll just first finish with the math. So when can we actually solve for this? What do we need in order to solve for u and v now? We need some condition, right, to be able to solve this equation. Yes? Right. So we definitely need A transpose A has to be invertible. So we want to, so we need to know when we can solve this to know if we can likely track a point. So one condition is that we need A transpose A to be invertible. If it's not invertible, then we'll have an ill-defined solution. So for example, if there were no gradients here, then we just have 0 times uv equals 0, and then it doesn't matter what u and v are, we'll still, with any uv, we'll still satisfy the equations. Another related constraint is that you don't really want A transpose A to be too small. So if the gradients are really small, then informally you can think of this as just noise is going to be determining your displacement. And so you're not going to actually get a good solution. And just mathematically, if they're small, then it just means that you're very sensitive, that the inversion is very sensitive to small changes. So if they were really small, then even like rounding error or like floating point errors could mess up your solution. And then likewise, you want it to be well conditioned. So if lambda 1 over lambda 2 is too large, so if eigenvalues, if one eigenvalue of this is much larger than the other, then it means that that your solution can easily be wrong around that direction. So what is this? So what is an interpretation of this? Where have we seen this recently? Yes? Right, this is the second moment matrix. And so what did we do with the second moment matrix? What? Yeah, I mean on Tuesday, we used the second moment matrix. Do you remember what we used it for? Right, we used it to define what points we want to track, right? So remember that on Tuesday we took the two eigenvalues, or we created a criteria that says that both eigenvalues of the second moment matrix should be large, right? That basically we said exactly that they should both be large and one should not be much larger than the other. That was kind of the Harris criteria. So the Harris criteria is specifically going to give you points that work well for this tracker. So let me then illustrate a little bit. It's on. So one thing, I don't know if you think about it, I think it is not intuitive. So think about the equation for a minute. What it's saying is that by looking at the gradient at time t, the gradient of intensity, and looking at the difference of intensity across neighboring frames, you can tell where the point has moved, right? So that's kind of surprising to me, because it's not that you're doing like some local search, which is what you might think of doing. You're just looking at that same position where the point was originally and seeing how the intensity changed and what the gradient was, and then saying, OK, based on that, it moved over here, right? So why does that work? So I don't know why it always has to, like, second guess itself.
Professor, I think there's a lamp there. If you turn it on, it might help.
Okay.
The other long thing, yeah.
Well, it does help with the lighting. I think maybe it'll settle on that. Okay, so let's do this come on. Let's do it in one dimension, right? Because one dimension is a little bit easier to think of. So basically it's like, why does the Taylor expansion work here? So you can think of this as your intensity, and this as your x direction. And so if I want to say, if I'm at this point, so let's call this A, and I want to predict or let's call this T, because this is really more like what we're doing. So let's say I want to predict what the intensity will be at time t plus 1 in this one-dimensional plot. So using the Taylor expansion, I would say that I at A plus 1 is equal to I at A plus T times IT of A. So it's just saying that I look at the derivative at this point, and I add that derivative, plus 1. Plus 1 times IT plus A, right? I look at the derivative at this point, and if I've moved one time step, then I just move length of 1 in the direction of that derivative, and that gives me a guess of my next position, right? So that's what it's doing. And so what is this actually doing? Another way to plot it is now let's say that I'm thinking of this as I've got some curve here, and then my curve moves to the right at the next step. So here, now I'm going to do this as the x-axis again. This is my curve at time t, and then the curve moves to the right. Okay, so this is t plus 1. So what it's saying is that the difference here, now where I have my intensity is in terms of x and t, the difference in the y direction is predictive of the difference in the x direction. Or sorry, the difference in time is equal to the difference of intensity that I observe between time steps at the same point is approximately equal to the difference that I observe between intensity that is approximately equal to the difference in motion that I observe between those time steps. So if you take some curve, as long as the intensities don't change, as long as there really is just a displacement in the x direction, then it's true, you can see from here that everywhere along this curve, the difference in the t direction is a good guess for the difference in the x direction. Now, of course, the exception would be if I imagine that my original intensities were like this, and then at t plus 1, my new intensities were higher everywhere, then obviously this wouldn't be a good way to estimate. But that's because all the intensities have changed. So I violated my brightness constancy assumption. So here, as long as we can assume that the brightness constancy, that the only change was that the points translated, then the difference of intensity of those points is predictive of the amount of translation. If there's a large difference of intensity, then it means that they probably moved a lot. If there's a small difference of intensity, then it means that they haven't moved very much. And then you also need to know the gradient, because if there's a steep gradient, then you would expect the intensity to change more quickly as the point moves than if there's a shallow gradient. So all the equation is really saying is that you can see from the gradient how quickly you'll see a change of intensity as the point moves. And then based on the amount of change of intensity and the change of gradient, you can guess how far it's moved. And based on a single point, you can't really tell where it's moved. But if you look at a whole set of points that has gradients in both directions, then you can tell how far those points have moved. Yes?
So this assumption doesn't cover any rotation, right? It just takes care of the linear transition?
Yes, that's right. So the statement was that so far this only covers translation. So I'm assuming that a point has translated, but I'm not dealing with any kind of rotation of the patch. Now, in practice, if an object rotates, then that can be dealt with approximately by saying that all the points on the object translate, but the points that are far away from the center of the rotation will translate more. So the reason why I don't usually have to really deal with rotation or more complicated changes is that I'm just looking at how a small patch has changed from frame to frame, and usually translation is enough to model that change of the small patch. I'll also note, though, that Lucas Canati also talks about, instead of just solving for displacement, you can solve for an affine transformation of the patch. You get more parameters that way. And that's often used for stereo, for like patchwise stereo, when you want to also estimate if you want to estimate depth and orientation, then solving for like the affine transformation of the patch can actually be useful. It's the same exact principle, though. You would just have the equation would change, but you still do it based on the Taylor expansion. All right, so here's another illustration of this concept. Or I guess it's an illustration of what points are good to track. So if you have a low texture region, then the gradients have a small magnitude. So you have small lambda 1, small lambda 2. Obviously, it's not going to be easy to track. If you are on an edge, then you've got a gradient that's large in one direction, but not the other direction. And so you're really only going to track the point somewhere along that edge, but it's hard to predict how far along the edge the motion is. And if you're in a high-textured region, then you have gradients in two different directions, and so then it's possible to estimate through this least squares solution. Another illustration is, remember this, how when there was just a line, we couldn't tell how the thing had moved. But now I'm hiding the edges again, and now you can see that it's moving down and to the right. So now the actual motion is the same as the perceived motion inside the aperture, because I've got gradients in two directions that I can use to disambiguate the motion. So even though we're not solving least squares problems most likely in our heads, but the math requires the math shows you the underlying ambiguity, and that ambiguity is true for us even if we're not solving it in exactly the same way. So one problem that you can have is that the Taylor expansion. So we're linearizing with the Taylor expansion, and remember that the full Taylor expansion has an infinite number of terms. And so you've got your linear term, and then you take like the second derivative and then the third derivative. And when we just take the first derivative, when we're doing the prediction of I of t plus 1 just based on I xyt plus the derivative and in each direction, then we're making a big approximation. And if there's a large change, then that approximation may not be very good. Or in other words, like if I'm trying to do this approximation and I've got a curve instead of a straight line, then my estimate is going to be off. So how do we deal with larger movements? One part of the solution, oh, question?
So effectively after the discussion, we come to our, like we want Ix and Iy to be both large. Is that?
Yes. So in order to track a point, we need there to be significant gradient, substantial gradient in both the x and y direction.
So if I have a strong edge along a 45-degree line, that splits into high Ix and Iy, but what's so sacrosanct about x and y direction that we are?
Oh, okay. So let me restate it. Actually, so we don't need actually a strong gradient in the x and y direction specifically. We need strong gradients in two orthogonal directions.
Which is always the case if we want to split a gradient. We might have a gradient in one direction. We can always split it into two directions and both being very high. Like a strong edge can be split into two perpendicular directions with both values high. Do you want the
No.
very well spread out?
So if I have a straight line, an edge like this, I can't. This only has one gradient direction.
That's a vector, right? I can split it into two perpendicular directions with both being high values. Do we need like well spread out gradients, or do we want high gradients in two directions? Because that's not a very rigorous constraint to have.
So it's if you, most precisely, you want the eigenvalues of the second moment matrix to be high. But what that means is that, or I guess a way of visualizing that is if you look at the direction of most, if you look at the direction where there's the strongest gradient and the direction that's perpendicular to that direction, then there should be gradients in both those directions.
But that doesn't materialize to having gradients high in two perpendicular directions, right? Those are not equivalent statements to me. You find the highest directions and then you find the directions perpendicular to it and see that. So that means that you have well spread out gradients. A texture has a well spread out gradient, whereas the edge has a very sharp gradient towards one direction. So we want more well spread out gradients than having gradients high in two directions, right?
Yeah, I think I see what you're saying, but I think that it's just I'm not sure how to say it. Yeah, so if you think about it, if you wanted to think about it that way, that's fine. So you need the edges need to be in different directions. That's the bottom line. So I think what you're saying is that if you computed a gradient that's not in the direction of the edge, you would still get a response from that gradient function, right? But what I'm saying is that the edge does actually have a specific orientation. There is a true gradient orientation for the patch, and so while you could project that onto multiple directions, I'm talking about the true gradient of the patch, yeah, the true direction of that gradient. All right, so how do we deal with larger movements? One solution is to do an iterative refinement. So basically, you do the Taylor approximation to jump to your guess of where the point is, and then you use that guess to do another Taylor approximation, and then you keep on jumping. And you can show that this will eventually converge to the true answer as long as the true answer is within some local minimum. So just to show what I mean by that, and then I'll do the math, or I'll go through that bullet list. So in this case, let me just draw again. All right, so in this case, where I make some guess on where the point is in the next step, and that guess is a little bit off, then I can make another guess, and then make another guess until I get to the correct answer. Let me just illustrate this a little bit differently. Let me go back to my pure one-dimensional plot. So if I'm here and I'm estimating the position of the next point based on the gradient, so here my guess is going to be a little bit above where the line is because, sorry, let me just get new paper. Okay. So I'm here. I estimate the position of the next point based on the gradient. And I'm a bit off in the y direction because it wasn't just a straight line. It actually curved on me. But then I can then take my estimate. I can then look to see where I am here. And then if I can tell that I'm a bit off, then I can make another guess and try to correct for it. And then I can keep on repeating that. Sorry, it's actually harder to illustrate than I expected before I tried to illustrate it. This PC. All right, so let's look at it here. Okay, so I initialize my x prime, y prime, which is my guess of where the point is at the next frame, with xy. And then I compute my guess of the displacement using the Taylor expansion in these equations. So I do the inverse of this matrix times this matrix, and that gives me an estimate of the displacement u and v. And so one thing to note is that x and y and x prime and y prime are not necessarily integers. I actually want to track at sub-pixel level. And so you need to do some bilinear interpolation to estimate the gradient values at that position. So now I've got some estimate of the displacement. And so now my next guess of where the point is at frame t plus 1 is x prime plus u and y prime plus v. So now I recalculate the gradient in the time direction. So I recalculate it, where I take the patch centered at ix prime, yi prime, minus the patch centered at ix prime, y prime, t plus 1, minus the patch ix, y, t. So ix prime, y prime, t plus 1, minus I of x, y, t. So only this difference of time, only the difference of intensity over time is updated. Because remember that when we computed the Taylor expansion at x, y, t, we're computing the gradient of the original intensity image at point x and y, which hasn't changed, right? So I only have to calculate the gradient in the x direction and the gradient in the y direction once per frame. And then I iteratively calculate the displacement, update my window in the second image, or in the next image, compute the difference of the intensities of the second window to the first window, and then recalculate the displacement and add that to my estimate. And in practice, you only need to do this a few times before it will converge. So in my implementation, I just say, like, do it 5 times. And that's usually fine. Otherwise, you could check to see if the change is small enough, then you stop. So let me I meant to show one more thing. So what are we doing? So here we have our image at frame t. We have the image at frame t plus 1. Ignore that a line is going through it. And then we've got our gradient image, ix. So this is just the gradient in the x direction. And our gradient image, iy, which is just the gradient in the y direction. So I've got some point here. Let's for now say it's a 5 by 5 window. And the same location in each of these. And then I've got initially my estimate of the, and so initially my estimate is that x prime, y prime is equal to xy. So I'm initially going to guess that it hasn't moved, and then compute this time difference. So my it is a 5 by 5 patch where I take the differences of the values of this window minus the values of this window. Ix is a 5 by 5 patch where I take the values of the gradients inside this window. And IY is a 5 by 5 patch where I take the gradients inside my X gradient image. Okay. So then I compute my second moment matrix. So I have my summation of IX, IX, summation of IY, IY, summation of IX, IY, same here. And this is equal to UV times minus summation of IX, IT, summation of IY, IT. So this summation is over all of the points inside this patch. And this summation of IXIT means that you take like the upper left value of IX and multiply it by the upper left value of IT, and so on. So sorry, IT is the difference between these two intensities. And so then that gives me some UV. So then I predict, let's just exaggerate the motion, that the point has moved to X prime equals X plus U, Y prime equals Y plus V. And so now my next IT is this patch where the point has moved minus the patch in the previous image at XY. This is exactly the same. This stays the same. But now the right-hand side of my equation changes because my IT has changed. And so then I estimate another displacement. And so then I get, then again, I update that X prime, let's call this U1 and V1 as my first estimate. Now X prime equals X plus U1 plus U2. Y prime equals Y plus V1 plus V2. And I, again, compute the difference of time, the difference of intensity across the two patches and the two frames, and then compute the displacement. Right, so that's the algorithm. Question?
When we get new UNV, do we add this set of UNV to the original location or the previous? Because we're keeping updating.
When you get the, oh yeah, so every time you compute the new UNV, you add it to your previous estimate. So that's why it becomes like, so when I said X prime is X plus U1 plus U2, it's the, you're accumulating the displacements.
Okay. And when we get the new XY, it is not necessarily integers, so we do integration every iteration.
Right. So when you get the new, so when you get the new XY, it won't be an integer typically, and so then you have to do interpolation. And so after the first frame, you typically have to do interpolation from then on because it's then a subpixel value. And actually, you might think that's not that important. You might be tempted to just like round off and save yourself the interpolation step. But actually, if you have even like an error of 1/4 of a pixel, that can lead to drift over time and cause you to latch onto the wrong point. You can imagine like if a point moves 1/4 pixel per frame, but you're just rounding off the values, then eventually you're not going to move your point at all, while eventually the point moves several pixels. Right. So so that's one method to deal. That's one way to deal with the large movement. So that lets us deal with the basically it lets us approximate Taylor or approximate the change by a piecewise linear series of approximations. Right. I'm doing Taylor approximation to linearize. And then I'm redoing the Taylor approximation at my previous guess to then make another step based on the linear gradients. So the other way that I can deal with larger motions is by using course-defined registration. So the idea is that you run LK stands for Lucas-Canati, which is the algorithm we've been talking about. So you run the iterative Lucas-Canati at course resolution. Then you upsample. So you predict that at twice the resolution, the coordinate has twice the value that it had at the coarser resolution. Then you run iterative Lucas-Canadi, and you upsample, and then you keep on doing that until you get to the full resolution, and then you're done. So I'll have an illustration of that in a moment. Although I'll have the illustration for optical flow, which I'll get to in a moment. Right, so all of this, the combination of what we talked about on Tuesday and now leads to the Shi-Tomasi feature tracker. So the idea is that you find good features using the eigenvalues of the second moment matrix. So it could be the Harris detector, or you could just threshold on the smallest eigenvalue. And the idea is that good features to track are ones whose motion can be estimated reliably. Then you track from frame to frame with Lucas-Canadi, which amounts to assuming a translation model for frame-to-frame feature movement. And then the final step of this tracker, which is in the Good Features to Track paper, is that you check consistency of the tracks by doing an affine registration to the first observed instance, which I'll illustrate in a moment. So affine means that you're encoding translation, rotation, shear, and scale. And this just helps you know if you've lost the track. So if you try to match it back to your original frame and the appearances don't line up as well, that means that you've got a lot of drift. And also the, And then the affine matching can also help correct the location. So this is just showing this frame is this sign is tracked over several frames. And this is showing the tracked window. And you can see that the sign has gotten a little bit closer or a little bit larger. And so there's a difference between the original patch intensity and this one. So in order to check to see if your track is correct, you do an affine warp, or you solve for the affine match between this patch and this patch, and then the intensities all line up. So you can see that it's a correct match. So this second row here is showing the window after doing the affine deformation. We'll talk about doing like affine alignments of images in a later class, but it's just a warping that accounts for rotation, scale, and shearing, as well as the translation. Question?
You have a matrix X, and you find AX equal to Y. You're using X and Y, and then you again multiply A with X to see how closely approximates Y.
So it's different. So this was found by solving for just a translation between the points. But then once you have that initial estimate based on a translation, you solve for an affine transformation that maps these intensities, that matches these intensities to these intensities. And so that affine transformation has more variables. It has six variables in it. And so you're able to get a better fit that way.
What I meant to ask is that you have the first image and the fifth one, and you find the best fitting affine transformation, which makes the first to the fifth.
Right.
Then how do you check? You multiply the first one with that affine transformation matrix, and you obviously have used the first and fifth.
So then you can just check to see if the sum squared difference between this patch and this patch is low. Then you've checked to see if you've matched it correctly. Where if you had lost the track, if this had drifted to another scene point, even after doing that affine transformation, the intensities won't match well. And so then you can see that you've lost the track. Okay, so here's a summary of, this is called Canadi-Lucas, or it's been, so the papers were Lucas-Canadi and Shi-Tomasi, but the tracker is called KLT, which is, I guess, Canadi-Lucas-Tomasi. So somehow Shi fell out of it. So you find a good point to track, for example, using the Harris corner detector. Then you use the intensity second moment matrix and the difference across frames to find the displacement. You can iterate and use coarse-defined search to deal with larger movements. And when you create long tracks, you can check the appearance of the registered patch or the displacement localized patch against the appearance of the initial patch to tell if your point has drifted too much and you've lost the track. So a couple of implementation issues are the window size, so how big should you make this patch? And basically the issue is that if you have a small window, then you're more sensitive to noise, and you also might miss larger motions. You can imagine that if the patch moves completely outside of the original window, then you have no basis for matching anymore. So, and this is especially true if you don't have a pyramid. So if you have a pyramid, then even if the patch is small in the original resolution, it will be larger as a proportion of the image size in the lower resolutions. So more pixels gives you more constraints, but you're also making an assumption that all the points will move the same within that patch. And so if for example, the large window crosses an occlusion boundary, meaning that part of it is on one object and part is on another object, that assumption will be violated, and that will also cause an error. So it's basically a trade-off between those factors. Typically, people use patches that are somewhere between 15 by 15 to 31 by 31. I suggest 15 by 15 for the homework problem. Another thing is that it's very common to apply weight so that the center matters more. And it all works the same way, except that when you're computing those sums, it's a weighted sum, weighted by some like Gaussian function that's centered at the center of the patch. So one thing that might occur to you is, like, why not, this seems fine, but why not just do local template matching? You could just take that original patch and then try to solve for the translation by matching that patch to the next frame. One major reason is that it's very slow. You'd have to search over a whole set of positions and do SSD. So this actually is extreme. It can be blazingly fast. You're only computing a few differences in order to localize the patch in the next frame. Another problem is that it doesn't give subpixel alignment, or if you did want subpixel alignment, then that local search would have to search over subpixels, so it would become even slower. So this is a really fast way to get subpixel alignment of the point. And but one thing to note is that if you expect that there may be really large motions, then it might make sense to do local template matching on some of the points to try to find those long-range correspondences. Question?
What is SSD?
Oh, SSD is sum of square difference. Thank you. So, so this is how you track a single. So we talked about how you track a single point. A related problem is called optical flow. That's solved in a very similar manner. So optical flow means how it's tracking how all the pixels have moved between two frames. So instead of tracking a single point, you're tracking all the pixels in an image. So this is illustrating basically like a forward motion. And so some points that are further away don't move very much. Points that are closer move more. Points that are like on the wall next to you will move the most in the image frame. So optical flow is a key way that we measure motion in images. And so, so one thing to note is a little bit about motion and perceptual organization. So optical, even if we have very limited motion data, it can give us a strong percept. So this is just an illustration of that. So this is kind of just an interesting aside. So here you've got like a set of points. It probably doesn't mean anything to you, but once those points go into motion, it becomes a person. And so this is just like a 2D projection of the 3D points that are on a person. In the same way, when we're estimating optical flow, we're not actually estimating a motion in 3D. We're estimating the projection of that motion on the image plane. But all of these motions can be very informative to us about objects that are moving and about our own motion. So we can use motion for many purposes, like estimating 3D structures, segmenting objects based on motion cues, doing learning and tracking in dynamic models, recognizing events and activities, and improving video quality. For example, like if you try to hold a camera still with your hand, it's very hard. There'll be like little motions between the frames. But if you estimate the motion between frames, then you can stabilize the video so that it looks like you had it on a tripod, basically. So there's a couple of important terms before I get to how to solve for optical flow. One is the motion field. The motion field is ideally what we would recover. So the motion field is the projection of the 3D scene motion onto the image. In this example, we have a rotating cube. And so it's rotating to the right. And so we'd get more motion for points that are close to us than points that are further away due to the perspective projection. So for example, if we had a ball moving towards the camera, then at the center of the ball, we'd have no motion. But at the edges of the ball, there'd be more motion as the ball expands. That would be the motion field. Optical flow is actually still not that motion. Optical flow is actually the apparent motion of brightness patches of the image. It's where the pixels with the same intensity go from frame to frame. So to see how that's different, you can imagine, for example, if a shadow moves across the wall, then we'll have optical flow where the shadow boundary is moving, even though there's no motion of the object itself. Or if you think about a sphere that's rotating under constant lighting, or a sphere that's stationary while the lighting is changing, you'll get apparent motion in both cases, even though the object's only actually moving in one of those cases. So it's important to just keep in mind that we're really measuring apparent motion, how the intensities change, not true motion. So to solve for optical flow, it's basically the same as Lucas-Canadi, except we're tracking all the pixels. And so this can actually be done really efficiently because we can do all the operations by we estimate the displacement at every pixel by solving the Lucas-Canadi equations using like a window at every pixel. Then we can just warp the entire image at time t to the image at time t plus 1 using the estimated flow field. And that's just done using an interpolation. And then we repeat. So we estimate the displacement at every pixel, warp the entire image to get our estimate of the patches at I t plus 1, and then keep repeating. So you could do a slightly slower implementation just by doing feature tracking for every single pixel by itself. But just the warping means that it's more efficient because you warp each pixel only once instead of for every window that it's in. So to do optical flow, you do coarse-define estimation. You create your Gaussian image pyramids for each image. You run the Lucas-Canadi, warp and upsample, warp and upsample, warp and upsample. So here's an illustration. Here's the original image. It's making some pretty large motions. Well, pretty large motions for frame to frame in this area of the tree. And so if I were to try to track this in the original resolution, I could lose the track because there's been motion of several pixels for the point. But if you look at the coarsest resolution, it's actually a sub-pixel motion. Right? It's not even moving by a whole pixel. It's just a fraction of a pixel. So I can track the point to the sub-pixel at the coarse resolution. Then I predict that the point moved by, say, half a pixel here, so it's moved by about a pixel here. And so then I can refine my estimate of the motion in the higher resolution. Then again, I can use that as a starting point for the higher resolution. And then again, I refine my estimate of the displacement until I get to the full resolution. So this is showing if I don't do the pyramids, if I just do an estimate based on the original resolution, then in areas where there's a lot of motion, which is where the tree trunk is, I get really messy, basically like garbage estimates of the displacement. In the areas where it's further away, I get better estimates of displacement because there's a smaller motion. When I do the pyramids, I get nice, consistent estimates of the motion. So all these arrows are pointing in the same direction, which is the motion of the tree in the image.
Warping, can you repeat that part again?
So warping just means that so we've estimated a displacement for every pixel. And to estimate how that has changed the intensities of the frames, you sample the values at that displacement for every pixel. So for example, imagine that every pixel has been displaced by 1 pixel to the right. Then your estimate of the intensity at t+1 will just be replacing every pixel with the pixel to the right of it. In practice, the displacement will be at subpixel levels and different for different pixels. So for every pixel, for every intensity at xy, you replace it with the intensity at x plus u, y plus v. And warping just so the warping is just basically replacing values with values at another position. So you can get errors in Lucas-Canati where the motion is large. One possible fix is that you could do some long-range key point matching to try to estimate those movements. You can get an error where the point doesn't move like its neighbors. And one way that you could try to fix that would be with more of like a region-based matching, so that you're not creating windows that fall on the edge of the image, but you're only looking, the edge of an object or region, but you're only looking within coherent regions to try to find the motion. You might get errors where the brightness constancy doesn't hold. So one improvement you can make is to try to match based on gradient constancy. And so all of these things are incorporated into this large displacement optical flow algorithm of Brox et al. Obviously, it's going to be a bit more complicated, but basically you start with something like Lucas-Canati. Then you do gradient constancy instead of intensity constancy. You do an energy minimization with the smoothing term to try to get more coherence in your motion estimates. You do region matching and key point matching to better match near the boundaries of regions and for long-range matches. So here you can see the estimate of displacement due to region matching. And so here, like, the color indicates the direction of movement, and the brightness indicates how much it has moved. You can see that it's pretty noisy because in these uniform regions you don't have much to go on, but it still gives you some kind of cue. Then you've got your pixel base, so this is like the Lucas-Canati type matching. It's very good in the upper body, which has only moved a little bit, but the legs, which are moving really fast, you don't have any information. And then key point-based matching, so that's adding the pixel base to the region base. Then when you add the key point-based matching, you can also track this foot, which has moved too much for the local matching. So using the combination, you can get a good estimate of both short-range and long-range motions. Right, so to summarize, we've seen major contributions from Lucas, Canati, and Shi. I probably shouldn't leave him out. Tracking feature points, doing optical flow. We can use the same thing for stereo, which we'll get to later, and structure from motion. And the key ideas are that by assuming brightness constancy and the truncated Taylor expansion equation leads to a simple and fast patch matching across frames if you don't have too large of a motion. And we can use course-defined registration to deal with more moderate-sized motions. Next week, remember that homework 1 is due on Monday. And next week, we're going to be talking about object and image alignment in class. Thanks.